In this video, we're going to talk about chemical bonding. So this is going to cover a couple of learning targets. We're going to start with I can describe how ionic compounds form. We're going to talk about their behavior and why they bond. So basically, a chemical bond is a force that holds two atoms together. They do that to satisfy that octet rule that we've talked about. Octet rule says that the atoms are going to tend to gain, lose, or share electrons to acquire a full octet. So of course octet means 8 valence electrons to be specific. And there's only one exception to this, and that's helium. But it only has the one energy level, so 2 valence electrons make it have a full octet. So we consider that a noble gas. Our learning target here is part of this all goes together. Sorry, y'all. So we're going to talk about all of these things. Let's talk about ionic bonds first. So we know that an ion is a charged particle. We have our cations, which are positive, anions, which are negative, and they form electrostatic attractions, meaning that opposites attract. And it actually forms a very, very strong bond. This happens between metals and nonmetals. So as you can see in this little picture here, sodium has 1 valence electron, which it donates to chlorine, which has 7. And what that does is it makes sodium have a complete octet from its inner electrons. Chlorine now has a full octet from its valence electrons. We have a positive charge, we have a negative charge, and these guys stick together because of that electrostatic attraction. In a covalent bond, the atoms are going to share electrons to form a complete octet. And this is going to happen between two nonmetals. So you can see that the blue electrons are from carbon. Carbon has 4 valence electrons from the periodic table. Hydrogen has 1. So we have 4 hydrogens sharing that 1 electron. Hydrogen is happy with 2 electrons because it has, it's just got the 1 energy level, same as helium. But carbon needs 8, so by sharing those 4 electrons with hydrogen, carbon satisfies its octet. Metallic bonding happens in metals. They form these crystal structures which are called lattices. And we call this a sea of electrons because the electrons are allowed to move freely between all of these positively charged ions. The electrons aren't bonded to any particular atom, so they can move around. And this is why metals are malleable and why they're ductile, why we can flatten them out and why we can put them into wires. Ionic bonding, the strength is going to determine the melting point and the boiling point. The stronger the attraction, the higher the melting point and boiling point. It's going to be harder to separate those ions. This forms rigid, brittle structures. It takes a whole lot more energy to separate those ions if they are strongly attracted. So the size is going to also affect the properties. The smaller ions are going to have more attraction, so they're going to have higher melting points and boiling points. Covalent bonds have a wide range of property due to what we call intermolecular forces. We're going to cover those in a later learning target. Basically, their boiling points and melting points are lower than ionic bonds because they don't have that electrostatic attraction. Metallic metals have pretty high melting points, boiling points. Not quite as extreme because the electrons can move, so it doesn't take a lot of energy to separate them. Boiling points, however, are high. We need lots of energy to make them happen. So like I mentioned before, those moving particles make them malleable and ductile. The strong attraction makes them very durable. And when we have a mixture of metals, we have what we call an alloy, like steel or brass or bronze. Those are mixtures of metals. Representative elements strive to be isoelectronic. Remember, iso means equal, so equal in electrons with our noble gases. So magnesium has 2 valence electrons. If it just loses 1, that's not a stable configuration, but if it loses 2, it becomes just like neon. Chlorine has 7 valence electrons, so if it gains 1, here we have our ion there. If it gains 1, it becomes just like argon, which is a stable electron configuration. Transition metals don't generally have noble gas configurations. but they do have a transition of electrons. So, for example, chromium has 4 electrons in the D. If it had 5, it would be half full. And you would have these orbitals. Remember, there's 5 d orbitals. Each orbital would be occupied. And that makes a relatively stable atom. So what it does is it takes one from the D and pops it over, or one from the S, excuse me, pops it over here into the D, so it's 4s1 3d5. Copper does the same thing. It's got 9, which is almost full, so it takes one from the S, and we have 4s1 3d10. Ionic compounds consist of formula units, which are pairs of ions. If the formula has a metal in it, then it is ionic. So sodium is the metal, potassium is the metal, magnesium, iron, those are all metals. These are all ionic compounds. If it has 2 ions, it's ionic. So if we have ammonium in here, ammonium chloride, ammonium sulfate, both of these things are ions, so it's ionic. So that's different from a covalent compound where you have nonmetal bonded to nonmetal. Like carbon dioxide, carbon and oxygen are both nonmetals. Nitrogen monoxide, nitrogen and oxygen are both nonmetals. Same thing for phosphorus tribromide. Acids have hydrogen ions, and H plus is always going to be your cation. You'll have hydrogen bonded to a nonmetal like hydrochloric, hydrosulfuric, hydrobromic, hydroodic, hydrofluoric. Or you'll have hydrogen bonded to a polyatomic ion like nitric, sulfuric, perchloric, phosphoric. But you can see all of these have this hydrogen first. Now if you have like H2 or H3, that comes from the charges. Using the electronegativity, you can determine if you have an ionic or a covalent compound. So you have to determine the electronegativity values. Those will be given to you in a problem. And then you just find the difference. So you just subtract. Magic number is 1.7. Now we say it's a magic number, but there is a little bit of leeway here. If it's greater than 1.7, it's ionic. If it's less than 1.7, then it's covalent. So here you can see kind of the progression from a pure covalent, which has a 0 difference in electronegativity. We have polar covalent. We'll be talking about what polar means. When you have a low difference, and then way over here, and like right here would be maybe 1.7, where you see a shift from covalent to ionic. I will give you this infographic in class, so you don't have to copy it and print it or anything like that. But this takes you through some of the stages. So a difference of about 0.5 is where we separate nonpolar from polar covalents. And then there's our 1.7, our magic number. We'll talk about the difference between intramolecular and intermolecular forces.